On the morning of January 16, 1943, the cargo ship SS Schenectady was moored peacefully in the port of Portland, Oregon. She was a brand new Liberty ship, no more than 10 weeks old, having just emerged from the Kaiser shipyards. There was no enemy threat, no storm battering her hull. The morning was quiet, the water still. Then, without warning, a sharp crack echoed across the harbor. Within moments, the ship's entire hull split clean in two. The structure fractured from deck to keel, as if sliced by an invisible blade. Sailors scrambled as the bow and stern sections sagged in opposite directions. Her back had broken while tied securely to the pier. The Schenectady was not alone. That same winter, the SS John P. Gaines split apart in a calm sea. The oil tanker SS Manhattan, built using the same methods, suffered a crack so severe that her crew abandoned her in a panic. Between 1943 and 1944, more than 2,500 Liberty ships reported serious structural failures. Cracks in the hulls, fractures in the decks, and catastrophic splits. At least 19 vessels broke completely in half. 3 simply vanished at sea, disintegrating so quickly they couldn't even send distress signals. These were not casualties of war. These were ships committing suicide. The United States had gambled everything on the Liberty ship program. After the attack on Pearl Harbor plunged America into a total war, the nation desperately needed cargo ships by the hundreds and fast. The traditional shipbuilding industry, a slow and laborious process, required many months to complete a single vessel. For instance, the SS Dorrington Court, a British ship similar in design to the Liberty ships but built with traditional methods, took a full 8 months to complete. At the height of the shipbuilding program in World War I, a ship only 2/3 the size of a Liberty ship required 10 to 12 months of work. Even the initial contracts signed by the U.S. Maritime Commission at the start of the emergency program specified 210 days to build each ship. The very first Liberty ship, the SS Patrick Henry, took 244 days from keel laying to delivery. The Maritime Commission could not wait that long. This is where Henry J. Kaiser, an industrialist who had never built a ship before, stepped in, promising something audacious. Cargo ships produced in massive quantities, built like cars coming off assembly lines in weeks instead of months. His shipyards in Richmond, California, used revolutionary techniques, welding instead of riveting, prefabricated sections instead of piece-by-piece construction, and assembly line logic borrowed from the auto factories of Detroit. By late 1942, Kaiser's yards were launching Liberty ships in an average of 42 days. The propaganda machines celebrated this industrial miracle. Newsreels showed images of Rosie the Riveter, though they were now actually welders, transforming steel plates into ocean-going vessels at impossible speeds. The SS Robert E. Peary set a record in November 1942, being built in just 4 days and 15 hours from keel laying to launch. Americans cheered. Finally, the Allied merchant fleet, decimated by U-boat wolf packs, had reinforcements pouring into the Atlantic. Then the ships began to fall apart, not from torpedo damage or heavy seas, but spontaneously and catastrophically in conditions that should have been routine. Naval engineers were baffled. The welds seemed solid. The steel met specifications. The designs were based on proven British plans. Yet, the Liberty ships were breaking like porcelain teacups. The cracks usually started at sharp corners, hatch openings, gun emplantments, and the boxy design of the superstructure. Once a crack began, it spread through the welded hull plates with terrifying speed, sometimes running the entire length of the ship in seconds. The Maritime Commission held emergency investigations, Metallurgists examined damaged sections under microscopes. Engineers rechecked stress calculations. Navy inspectors crawled through the halls with measuring tools. Everyone was searching for the culprit: bad steel, faulty welds, design flaws, or inadequate quality control. The ships kept splitting while the committees debated. Sailors grew terrified of their own vessels, knowing that the hull beneath their feet could open up without warning in the cold Atlantic waters. The miracle of mass production had turned into a naval nightmare, and no one could explain why the ships built in record time were falling apart in record numbers. The answer came from the most unexpected source imaginable: from a female welder on the assembly line who was not supposed to question engineering decisions. She worked the night shift at Kaiser Shipyard No. 3 in Richmond, one of thousands of women who had flooded into the shipyards after the men went overseas. She had been welding hull sections for 8 months, long enough to notice something that the engineers apparently had not. Every night, she watched her team weld massive steel plates in a sequence that made no mechanical sense whatsoever. She saw welders starting from the edges of the plates and working inward, or starting at one end of a long seam and proceeding straight to the other. With each cooling weld, the metal contracted, pulling and distorting the plates. She could see the stress building up, watch the steel warp under her torch. When the welders finished one section and moved to the next, they were actually locking that stress permanently into the hull. It was like tightening the center lug nuts on a car wheel before securing the outer ones, a recipe for imbalance and failure. Her supervisor dismissed her concerns. She was a welder, not an engineer. The sequence came from the engineering department, from men with university degrees and training in naval architecture. But she persisted. In November 1943, she demanded a meeting with the yard supervisors, bypassing the chain of command in a move that could have gotten her fired. She brought samples with her, test plates she had welded in her spare time using different sequences. Some showed significant warping and obvious stress patterns. Others, welded from the center outwards in a carefully planned sequence, were flat and true, with minimal distortion. The supervisors were skeptical but intrigued. One agreed to observe the production line during her shift. What he saw confirmed her observations. The welders were essentially torturing the steel, forcing it to accept stresses it would carry for its entire service life. Every cooling weld created residual tension in the metal. The construction sequence meant these internal stresses were accumulating and concentrating at specific points, especially at the corners of hatches and other stress concentration points. When these ships hit the cold waters of the North Atlantic, the steel became brittle. The locked-in residual stress, combined with the brittleness, created the perfect conditions for catastrophic fracture. Her insight was simple and elegant. Weld from the center of the sections outwards, allowing the stress to dissipate toward the edges rather than concentrating in the middle. Alternate welding positions to prevent heat buildup in one area, and never complete welds in long, continuous runs. Instead, use a balanced sequence that distributed the cooling stresses evenly. These were not revolutionary metallurgical theories. They were practical observations from someone actually working with the material every day. Someone who felt the metal move under her torch and understood the consequences. By December 1943, her observations had reached Henry J. Kaiser himself. He faced a stark choice. The Liberty Ship program was already under congressional scrutiny for the cracking epidemic. Admitting that the construction sequence, not the steel quality or weld integrity, was the fundamental problem meant acknowledging that every ship built to date had a systemic flaw in its structure. It meant temporarily slowing down production to retrain thousands of welders. And it meant redesigning the entire assembly process. But it also meant potentially solving the fracture crisis that threatened to undermine the entire American maritime supply chain. Fortunately, Kaiser did not hesitate. He ordered immediate tests of her theories, pulling an entire hull section from the production line for an experimental rebuild. The metallurgists and engineers who had spent months analyzing broken ships were now taking instruction from a night shift welder who had never seen the inside of a university classroom. The test results were both conclusive and revolutionary. When Kaiser's metallurgists examined the hull sections built using the traditional sequences versus the welder's methods, the difference was measurable and dramatic. Residual stress gauges showed that the traditional welds carried internal tensions exceeding 30,000 pounds per square inch, concentrated at key structural points. The sections welded with her sequence distributed those stresses over wider areas, with peak readings barely reaching 12,000 pounds per square inch. The steel itself was identical. The welds were chemically indistinguishable. Only the order of operations had changed, yet the structural integrity had improved by factors that engineers initially refused to believe. The physics behind the failures finally became clear. Steel is not a static material. It is a crystalline structure that responds dynamically to temperature changes. When a welder runs a torch along a seam, they create a localized temperature exceeding 2,500 degrees Fahrenheit. The metal expands significantly in that hot zone. As the weld cools, it contracts, but the surrounding cold steel restricts this contraction. The result is a residual tensile stress permanently locked into the structure unless the welding sequence allows for stress redistribution. The Liberty ships were suffering from what metallurgists call brittle fracture propagation. The steel used in their hulls, a carbon steel intended for shipbuilding, performed well in warm waters, but it underwent a critical transformation in the near-freezing temperatures of the North Atlantic. Below a temperature of about 40 degrees Fahrenheit, the steel's ductility collapses. Normally, the metal absorbs stress by deforming slightly, bending rather than breaking. But cold steel loses this flexibility. It becomes brittle, more like glass than the tough material the welders had worked with in the mild California shipyards. When brittle steel meets a concentrated residual stress at a sharp corner, like the square edge of a cargo hatch, physics takes over with brutal efficiency. A microscopic crack begins. In ductile steel, this crack would stop, absorbed by the material's ability to yield. In brittle steel, under tension, the crack becomes a runaway fracture. The energy stored in those residual stresses provides the fuel for the crack's propagation. The sharp corners act as stress concentrators, multiplying the local stress by factors of 3 or more. The crack accelerates, sometimes exceeding the speed of sound in steel, spreading across the hull before bulkheads or frames can stop it. The fracture of the SS Schenectady made perfect sense in hindsight. It had been built in early winter, welded with sequences that maximized residual stress. Its hull carried tens of millions of pounds of locked-in tension. When the temperature on that Portland morning dropped to 28 degrees, the steel became brittle. The stress concentration at a hatch corner initiated the crack. That crack found a straight path across the continuously welded deck plates. There were no riveted seams to slow it, no stress relief joints to stop it. The fracture consumed the ship in seconds, releasing decades of stored energy in a single catastrophic failure. Traditional riveted ships did not suffer from this problem, and the reason explains why welding seemed cursed. Riveted construction is inherently discontinuous. Each riveted plate is a separate element. Cracks that start in one plate hit a rivet line and stop. The overlapping plates and mechanical fasteners create natural crack barriers. Welded ships, however, are continuous structures. A crack in one plate can run unimpeded across hundreds of feet of fused seams. The very efficiency that made welded shipbuilding faster also made it vulnerable to failures that riveted ships could not experience. The boxy design of the Liberty ships exacerbated the problem. British naval architects had specified those sharp corners to facilitate cargo loading. No one had considered that sharp internal corners create stress concentrations that multiply applied loads by huge factors. Every wave that flexed the hull sent stress surges through those corners. Combined with the residual welding stress and the brittle steel, those corners became crack initiation sites, waiting for the right conditions for catastrophic collapse. Henry J. Kaiser understood what the test results meant for his empire and the war effort. In January 1944, he made a decision that would either vindicate his industrial revolution or expose him as a reckless contractor who had sent thousands of sailors to sea in flawed vessels. He ordered a complete halt to Liberty ship production at Richmond Shipyard No. 2 and shifted resources to an entirely new class of vessel, the Victory ship. This was not a minor modification. It was a fundamental redesign based on the welder's observations and the hard lessons written in broken hulls across two oceans. The gamble was immense. The need for Liberty ships was desperate. U-boats had sunk over 2,000 Allied merchant vessels since 1939. The invasion of Europe, still months away in early 1944, would require the largest amphibious logistics operation in human history. Every ship counted. Yet Kaiser was betting that he could implement the sequenced welding system, redesign the hull to eliminate stress concentrations, upgrade the steel specifications, and somehow maintain production speeds that already seemed miraculous. His competitors thought he had lost his mind. Congressional investigators sharpened their knives, ready to crucify him if production collapsed. Kaiser's engineers worked backward from the failure points. Every square corner in the Liberty design was replaced with rounded curves. The hatches that had been the source of so many cracks were redesigned with a large radius, eliminating the stress multipliers that turned normal loads into fracture initiators. The thickness of the deck and hull plates was recalculated, not to add strength, but to ensure that the stress distribution matched the new welding sequences, and the structural frames were repositioned to align with natural stress relief points rather than fighting against the welding pattern. The steel itself changed. Kaiser's metallurgists specified a new alloy with improved toughness at low temperatures. The carbon content was slightly reduced and the manganese content increased. Small additions of nickel, which had been expensive and reserved for armor plate, were justified by demonstrating that a 0.25% nickel content dramatically improved the steel's resistance to brittle fracture. The Maritime Commission balked at the cost until Kaiser presented calculations showing that preventing the loss of a single ship would pay for the upgraded steel in 50 vessels. In March 1944, the new steel specification was approved. Then came the massive task of retraining the workforce. The Richmond shipyards employed over 90,000 workers by early 1944. Thousands of them were welders who had learned their trade in intensive weeks-long training courses, mastering just enough technique to lay straight beads at production speed. Now, they needed to understand sequencing, stress relief, and thermal management. Kaiser established in-yard welding schools, pulling experienced welders off the line to teach others. Every welder was issued a numbered sequence card for each section of the hull. Weld number 1 here, number 2 there, never deviating from the prescribed order. The prefabrication system expanded dramatically. Instead of welding large sections on the slipways where sequencing was difficult to control, Kaiser's planners broke the Victory ships down into smaller modules built in specialized shops. A bow section might have 50 pre-assembled sub-assemblies, each welded in controlled conditions using the optimal sequences, then stress-relieved in heating furnaces before final assembly. This modular approach meant that welders could work from the center of each small section outwards, just as had been demonstrated, without the constraints of assembling an entire hull. The skeptics had ammunition when the first Victory ship's keel was laid in February 1944. The build took 18 days, slower than the Liberty ship records. Kaiser's yards were no longer performing miracles, they were just building ships at impressive speeds. The second Victory ship took 16 days. Critics declared the program a failure, proof that quality and speed were incompatible. Kaiser ignored them. He was watching the crack inspection reports, not just the build times. The first 2 Victory ships showed no stress cracks in their post-construction inspection. Not fewer cracks, but 0. By April 1944, Richmond Yard No. 2 had transformed into a precise ballet of steel, fire, and human coordination that would have seemed impossible 2 years earlier. The yard no longer looked like a traditional shipyard. It resembled a massive assembly plant, with distinct manufacturing zones feeding a central assembly area where holes took shape with breathtaking speed. Kaiser borrowed Henry Ford's concept of the moving assembly line, but instead of the product moving, specialized teams rotated through fixed construction stations on a timed schedule. The process began in the prefabrication sheds, huge covered structures where welders worked on hull sections no larger than 30 feet in any dimension. Each section had a specific sequence card. A bottom plate assembly might require 47 individual, numbered and color-coded welds. Welders started at position number 1, always the geometric center of the section, and worked outwards in a spiral or radial pattern. Supervisors walked the floor with checklists, ensuring no one skipped a step. After every 10 welds, the section would go into a stress relief furnace, where it was heated to 2,100 degrees and then slowly cooled. This annealing process allowed the steel's crystalline structure to relax, dissipating the residual stresses before they could accumulate to dangerous levels. The steel itself arrived pre-cut and pre-formed from rolling mills, retooled specifically for Victory ship production. Unlike the Liberty ships, where workers cut and shaped plates on site, Victory ship components arrived ready for immediate assembly. The curved bow sections came pre-formed to the exact specification. The deck plates had pre-drilled bolt holes for temporary alignment. The frame sections were pre-welded sub-assemblies. This preparatory work done in controlled factory environments eliminated variables and ensured consistency across thousands of components. Assembly on the building ways followed a radically different sequence than Liberty construction. Instead of starting from the keel and building upwards, the Victory ships were assembled in large modules that came together almost simultaneously. The engine room section, the cargo hold sections, the bow, and the stern were all built in parallel, then lifted by massive gantry cranes and put into place in a single coordinated operation. On May 12, 1944, Yard No. 2 executed its most ambitious assembly yet. 17 major modules, representing 85% of the complete hull, were placed and aligned in just 11 hours. Welders then connected these modules using the same center-out sequences, but now they were joining stress-relieved sections instead of building stressed sections from scratch. The 5-day timeline became a reality through the relentless optimization of every minute. Night shifts pre-positioned materials for the day shifts. Specialized teams did nothing but inspect alignment and weld quality, catching errors before they propagated. Mobile cranes moved on scheduled routes, delivering components to welding stations within 5-minute windows. Welders worked in relays, 30 minutes on the torch, 10 minutes off, maintaining consistent quality without the fatigue-induced errors that had plagued marathon welding sessions. Kaiser implemented what he called the critical path method, tracking which tasks were bottlenecks and which could run in parallel. If framing was ahead of schedule but pipe fitting was behind, he would shift workers immediately, maintaining equilibrium across all construction phases. Every delay, every deviation from the schedule was documented and analyzed. Morning meetings reviewed the previous day's performance, identifying solutions before minor problems became catastrophic delays. The record came on June 27, 1944. The SS Benjamin Warner, Victory Ship Hull Number 23, was completed from keel laying to sea trials in 5 days and 11 hours. It was not a stripped-down demonstration vessel, but a fully combat-ready cargo ship, complete with defensive armament, full electrical systems, a running engine room, and every rivet, or rather every weld, executed according to the new stress relief protocols. It carried 0 hull cracks. Its post-construction inspection revealed stress levels well within normal operating ranges. When the Warner sailed on her shakedown cruise, she performed flawlessly in conditions that would have broken the early Liberty ships. The 5-day Victory ship was not just about speed. It represented a complete rethinking of how to manufacture complex machines when engineering principles align with the practical realities of construction. The observation of a single welder had transformed into a systemic shift in industrial shipbuilding. The Victory ships that emerged from Kaiser's redesigned production system were fundamentally different vessels from their Liberty ship predecessors. Although casual observers saw similar-looking cargo haulers with identical missions, the differences began at a molecular level and extended through every aspect of design and construction. While Liberty ships were emergency stopgaps, Victory ships were engineered solutions that addressed every failure mode written in the blood of the sailors who had ridden cracking hulls into the cold Atlantic. The improved steel specification proved critically important. The new alloy, called a killed steel because aluminum was added during production to remove oxygen, showed dramatically improved toughness at low temperatures. Laboratory tests demonstrated that the transition temperature, the point at which the steel shifts from ductile to brittle behavior, had dropped from around 40 degrees Fahrenheit in the Liberty ship steel to nearly 5 degrees. This 35-degree improvement meant that Victory ships retained their structural flexibility in conditions that turned Liberty hulls into fragile shells. The added cost was 8% per ton, but the performance gains were incalculable. Every structural detail reflected the new understanding of stress concentration and crack propagation. The rounded corners of the hatches, a seemingly minor aesthetic change, reduced local stress concentrations by more than 60%. Engineering calculations showed that the sharp 90-degree corners on the Liberty ships created stress multipliers of 3.5 to 4 times the nominal hull stress. The large radii of the Victory ships kept the stress multipliers below 1.8. In practical terms, this meant that a wave impact that might start a crack in a Liberty ship would only flex the hull of a Victory ship within normal elastic limits. The hull plates themselves were installed with crack arresting features built into the structure. Instead of continuous welds running for hundreds of feet, the Victory ships incorporated riveted seams at strategic intervals. These hybrid connections provided deliberate discontinuities, places where a crack propagating would hit a mechanical joint and lose its energy, potentially stopping it before it could consume the whole hull. It was defensive engineering, planning for failure modes rather than assuming perfection. The structural frames were doubled at critical stress points, creating redundant load paths. If cracks developed in one frame, the adjacent frames could carry the load until repairs could be made in port. Liberty ships had no such redundancy. The failure of a single frame often led to a cascading collapse as loads were redistributed to already stressed adjacent structures. Victory ships could sustain damage that would have sunk a Liberty ship and remain operational, limping into port with damaged but functional structures. The welding sequences developed from the welder's observations were codified into detailed procedures governing every joint in the ship. The procedure manuals ran to hundreds of pages, specifying not just the sequence, but the thermal management between welds. Welders learned to monitor the interpass temperature, the heat level of the base metal between successive welding passes. If the steel exceeded 400 degrees, work stopped until it cooled naturally. This prevented the cumulative heat buildup that had caused massive distortion in Liberty ship construction, where welders sometimes worked continuously on long seams, superheating the steel and locking it into warped, stress-filled configurations. Quality control became an obsession. Every completed weld underwent magnetic particle inspection, a technique where iron powder and magnetic fields reveal microscopic cracks invisible to the eye. Ultrasonic testing checked for internal weld quality, ensuring full penetration and no hidden voids. X-ray inspection examined critical structural welds, producing permanent photographic records of weld integrity. Ships were not launched until inspectors certified that every weld met specifications. The rejection rate was high at first. Nearly 15% of welds failed inspection on the first few Victory ships. But the welders learned quickly. By mid-1944, the rejection rates had fallen below 3%, a testament to the training programs and the clarity of the new procedures. The proof emerged in operational service. Between June 1944 and the end of the war in August 1945, 531 Victory ships entered service. Not one of them suffered a catastrophic hull failure. Minor cracks appeared in a handful of vessels, stress concentrations that inspection caught before they could propagate. These cracks were repaired using the same stress relief welding procedures, and the ships returned to service. The contrast with the Liberty ships was absolute and conclusive. The human calculus of Victory ships versus Liberty ships played out across two oceans in 1944 and 1945, written in lives saved and missions accomplished that would have ended in disaster with the earlier vessels. The SS Mandan Victory, a Victory ship, struck a mine off Okinawa in April 1945. The explosion blew a 20-foot hole in her hull below the waterline. The crew braced for the catastrophic crack propagation that had killed Liberty ships. Instead, the fracture stopped at the first riveted crack arrestor seam. She made it to port on her own power, was repaired in 6 days, and returned to service. A Liberty ship suffering similar damage, the SS Richard Hovey, took a similar mine hit in February 1945, cracked longitudinally for more than 90 feet, broke her back, and sank in 14 minutes with the loss of 37 crewmen. The logistics of the Pacific campaign were impossible without the reliability of the Victory ships. By June 1944, American forces were advancing across the Central Pacific toward the Philippines and eventually Japan. Each island advance required millions of tons of supplies moved across thousands of miles of ocean. Liberty ships could make the journey, but their structural fragility meant reduced cargo loads in heavy seas, slower transit speeds to minimize hull stress, and the constant risk of catastrophic failure far from any rescue. Victory ships operated at full loads at their designed 15-knot speed, 3 knots faster than the Liberty ships, through typhoon-prone waters without the paralyzing fear that a cold night and a heavy sea would split the hull. The numbers told the story. Between D-Day in June 1944 and VJ Day in August 1945, Victory ships transported over 18 million tons of cargo with 0 losses due to structural failure. They operated in North Atlantic convoys where water temperatures routinely dropped below 35 degrees, the conditions that had fractured dozens of Liberty ships. They sailed the Arctic routes to Murmansk, carrying Lend-Lease supplies to the Soviet Union, where near-freezing seawater temperatures made Liberty ships terrifyingly vulnerable. The SS Hobart Baker, a Victory ship, made 17 trips to Murmansk without a single stress crack. The Liberty ship John Walker, on the same route, developed cracks on her second voyage and was permanently pulled from Arctic service. Crew morale transformed as sailors transferred from Liberty ships to Victory ships. Oral histories collected after the war revealed the psychological toll of serving on vessels known to spontaneously collapse. Merchant mariners reported constant anxiety, especially in cold weather. Sleep was difficult when every groan of the hull might signal an imminent fracture. Some sailors requested transfers or simply refused to sail on certain Liberty ships with known cracking histories. The Victory ships restored confidence. Crews pushed these vessels hard because they could take the punishment. That confidence translated into mission effectiveness, faster turnaround in port, a willingness to sail in marginal weather, and aggressive maneuvering when under air attack. The economic calculus was brutal but clear. Each Liberty ship cost approximately $2 million to build. Victory ships cost $2.6 million, 30% more expensive. But a Liberty ship had a 4.6% chance of suffering a catastrophic structural failure during its service life based on the actual failure rates through 1944. Those failures killed an average of 18 crewmen per incident and destroyed cargo worth 3 to 5 times the construction cost of the ship. The 0 failure rate of the Victory ships meant that the extra $600,000 construction cost was recouped within the first 6 months of service simply through risk elimination and reduced insurance premiums. By the end of the war, merchant mariners had a grim saying that captured the difference. Liberty ships were built by the mile and chopped off by the yard. Victory ships were built by the inch and measured by the year. Those inches, the meticulous attention to stress relief sequencing, the obsessive quality control, the engineered crack arresters, meant decades of service life instead of desperate prayers every time the hull groaned in a cold sea. The Welder returned to civilian life in 1946 with no fanfare or recognition beyond a letter of commendation from her shipyard supervisor. She never received a medal, never testified before Congress, never saw her name in the technical papers that later documented the welding revolution she had sparked. The engineering establishment absorbed her insights, reframed them in mathematical language and academic terminology, and published them as if the discoveries had emerged from laboratory research rather than the practical observation of a night shift welder. For decades, welding textbooks taught stress relief sequencing without mentioning the woman who had first recognized its necessity while watching hull plates warp under her torch. Yet her legacy permeates modern engineering in ways that extend far beyond shipbuilding. Every welded structure built today, from skyscrapers to pipelines to pressure vessels, follows sequencing protocols that descend directly from the procedures developed at the Richmond shipyard in 1944. The American Welding Society's Structural Welding Code, first published in 1947, codified the center-out welding sequences and stress relief requirements as mandatory standards. The construction of the Trans-Alaska Pipeline in the 1970s relied on welding procedures that explicitly referenced Victory ship methods to prevent cold weather cracking in Arctic conditions. The 800-mile ribbon of welded steel carrying hot oil across sub-zero temperatures exists because engineers understood the lessons the welder had taught. Modern bridge engineering inherited the same principles. The catastrophic failure of the Point Pleasant Bridge in West Virginia in December 1967, which killed 46 people, implicated residual welding stress as a contributing factor. The investigation revealed that welds performed without proper sequencing had locked stress concentrations into the structural members. The code revisions after the disaster mandated the sequencing and inspection protocols that the Victory ships had pioneered. Every welded bridge built since integrates those requirements. The Victory ships proved that the sequence of manufacturing is as important as the choice of materials or the structural design. Modern engineering curricula now include manufacturing processes as core components of design courses. Engineering students learn that a perfect design executed with a poor fabrication sequence produces inferior results compared to a modest design built with proper procedures. The 5-day construction timeline, while impressive, was never the real achievement. Kaiser's yards could have maintained Liberty ship speeds indefinitely, launching defective vessels that looked seaworthy until they fractured. The actual miracle was slowing down enough to do it right, having the courage to halt production and redesign processes based on a welder's insight that contradicted established practice. That willingness to listen to frontline workers, to admit that engineering theory had missed something crucial, to redesign systems around observed reality rather than defended assumptions. That was the revolution. Every modern manufacturing methodology, from Six Sigma to lean production to total quality management, embeds that principle. The worker observing the process often sees what the engineer calculating from a desk cannot. The welder died in 1987, her obituary mentioning only that she had worked in the wartime shipyards. But every welded structure standing today, every pipeline crossing frozen terrain, every pressure vessel containing dangerous forces, every bridge spanning rivers, all of them carry her legacy in their sequenced welds and stress-relieved joints. A silent testimony to the welder who asked why the ships were breaking and refused to accept "that's how it's done" as an answer.